All right, so now we're back. I want to go through and see if we can exercise some of the stuff that we were just reviewing with an example, okay? Now, this example is probably one we're going to refer to a number of times in the class, this cross-section. It's a pretty generic but straightforward cross-section that we can use for a number of examples. So let's go through a couple things just to ensure we're all clear on the parameters. So we've got a bridge that has 4 beams. They're all spaced at 10 foot on center. So that's the center of the web on each beam that's 10 foot apart. The overhangs on each end are 3 foot 6 inches. So the overhangs from the center of the web to the edge of the slab, so that's 3 foot 6. What's my haunch? Let's see if y'all can see that. See if y'all are paying attention. 2 inches. So 2 inches from the top of the web to the bottom of the slab, right? Okay? Now I have an 8.5 inch slab, but 1/2 of an inch of that I'm going to assume is worn away, okay? So structurally, my slab is how thick? 8 inches. Later on, if we go look at loads, we would consider 8.5 inches, okay? Sound good? Okay, all right. We've got typical concrete parapets on this. We have a 34-foot wide roadway, which I didn't really mention this, but as bridge engineers, we recognize that there are these painted lines on the road that tell trucks where to go, but really don't care where they are, because when we do our load placement, we place our trucks in the worst position possible. So yeah, there's paint on the road, but we don't really care where the traffic lanes are. It's all about where the structural lanes are. All right. So this is a cross. All right. So this is the cross section of the bridge. Anybody have any questions about this? Okay. All right. Let's look at the beam. So this is looking at the beam on the side. So this is a 2-span bridge. It's 90 foot long. You notice that the beam has a series of transitions, which is very common in steel girders, that you don't use the same flange sizes and the same web sizes throughout. If you look in the center of the girder, well, if you look at the webs, let's just do that. The webs, they have the same depth, but you notice that it gets thicker around the pier. So the web is 42 by 7/16 inches in all the positive bending regions, but around the pier, they had to bump that web thickness up 1/2 of an inch. That's because the shears get a little larger right there around the pier. Top flange, it's 14 inches wide across the board, but it gets thicker, okay? Now that's very subtle, a subtle point that the top flange has the same width, but that is incredibly economical in terms of fabrication and erection, because having the same top flange width makes the fabrication of that top flange a whole lot easier, and it makes the installation of form work a whole lot simpler, okay? Making the top flange wider in the middle of that girder as opposed to thicker would substantially increase the cost. So, but we'll talk about that later. The bottom flange, however, is the same across the board. It's all 1 1/4 inch, all right? Any other questions? Now, there's a framing plan associated with this where we look at cross-frame layouts and what have you. We really don't need that for what we're talking about right now, so I just sort of left that out. All right, sound good? All right. Now, for this example, we are going to use a little bit of Microsoft Excel to sort of simplify some of the counts that we do. I'm going to draw a little bit of some diagrams here there to clear it up, but we're going to use Excel. If you're unfamiliar or you haven't used it in a while, again, I'm recording this, so you can always go back and review what it is that I did. But this is pretty basic stuff. All right. Sound good? Okay. All right. So let's start off. Let's look at the positive bending region. Okay. And I might need some of y'all's help, so bear with me. All right. Let's look at the positive bending region. And I'm just doing this for the purposes of clearing up what I do later. I can do a little better than that. It's been a while since I used this, so. Y'all read that? That look good? Okay, all right. So the positive bending region, if I look at, let's start off looking at just the steel by itself. So the steel only section. So this is the section that would have to resist the weight of the wet concrete, the self-weight of the girder itself, cross frames, the studs, all those details, the formwork. That's what the steel girder itself would have to resist. And it is a girder that is, it's an I-beam. And what was this? Let's put some dimensions on here. This was what, 14 by 3/4? Is that right? All right. This is 42 by 7/16, and this is what is it? 16 by 1 1/4. All right. Sound good? All right. Now I'm going to build an Excel sheet that's going to compute some relevant section properties for this, but I want to make a couple points. You all remember, or it might have been a while, and that's fine, but you all remember the concept of computing a centroid, right? Remember, the sum of AY over the sum of A will give you where the centroid is. When you compute a centroid, you have to compute it by referencing your distances about a given point, okay? So what I'm going to do is I'm going to create an imaginary point to where we'll start to reference our distances. And I'm going to call that the datum, okay? It's a pretty fancy word, but basically what I'm going to do is when I calculate all of my y distances, I'm going to reference them from the very bottom, okay? And you'll see how we use that here in a second. That's number one. Number two, I'm also going to try and be fairly diligent in creating an Excel spreadsheet that's easy to manipulate. In other words, if I change that bottom flange dimension to be 1 inch thick, I want it to automatically update everything else, okay? That's what Excel is good for. That's what it's good for, okay? So, sound good? All right. So I'm going to leave this here for now, and I'm going to jump into Excel. All right, sound good? So now I increased the font in Excel, so hopefully you all can see what I'm about to do. All right, so let's go into Excel. Okay, so what I'm going to do is I'm going to enter in some dimensions. So we'll say top flange, web, and bottom flange. So I'm in Excel, and let's see what we can do here. So we'll say width, we'll say thickness. And you all can organize this however you want when you do your own sheets. I mean, you can organize it however you want. I'm just doing it for clarity here. Let me sort of center that up. All right, so what do we had? We had a top flange that was 14 inches wide, and it was 0.75 inches thick, right? And we said our web was 42, and this was 7/16, right? Sound good? All right. Bottom flange, 16, 1 1/4. All right. What I'm going to do is I'm going to highlight these cells. I'm going to make them like yellow or box them up a little bit. What I'm going to do is I'm almost going to treat this like it's one big computer program. I'm going to say that's my input, okay? So by changing those values, I want it to change everything else, okay? I want every one of my calcs in some way, shape, or form to reference that. Sound good? All right. Now, I'm going to draw myself a little table here, so bear with me. So let's see, shape. And I'm going to fill in a couple things, just bear with me. I've done this so many times, I sort of have this memorized. And you'll see why I'm doing this here in a second. All right, let's see if I can format that up a little bit. We'll zoom out. So this is just me making it pretty and easy to follow. And let's shade that. All right, can you all read that? Did that come out pretty well? Okay, all right. So what I've done is I've created a little table, and I'm going to use this table to compute some section properties. Okay. Now, in order to simplify what it is that you see here, these first three columns are largely going to be used to calculate the centroid, and the last three are going to be used to calculate the moment of inertia. Okay. So let's start off with the first column, the area. I want to calculate the area of each individual component. So let's just get back to basics. What's the area of the top flange? There we go. Now, instead of typing in equals 14 times 0.75, I'm going to do equals this times that, right? And then I can just copy and paste that down. Just Control-C and Control-V, and now it's calculated the area of each element, okay? The point being, if I go in and I change this bottom flange to 1, now it updates it, okay? And that's going to be a really critical parameter of everything that we do this semester. We're basically building these really fancy calculators that will do what we tell them to do. So we really want to take the reins and make them do what we want. I mean, you're the engineer. Build the sheet the way you want to use it, okay? I'm just doing this for the purposes of demonstration. When you do it, you do the way you want to do it. That's the nice thing about Excel. You can use it however you want. Okay. Let's take some time to talk about these Y distances, okay? So I'm going to go back to this, all right? These Y distances are the distances from the datum to the centroid of each shape. Okay, so remember, these are rectangles, so let's go back to statics. The centroid of that rectangle is about right there, halfway up, right? Centroid of that, about right there, and about right there, right? Best I can draw here on the screen. So, help me out. If I'm referencing all the distances from the datum, how far is it from the datum to the centroid of, say, the bottom flange? How do I get there from the datum to the centroid of this? What do I do? Half of this, right? Sound good? Now, how do I get from the datum to here? There you go. Go the 1 1/4 and then half of that, the 42, right? How do I get here? I go that, the 42, and then half the 3/4. Sound good? Okay, all right. So, let's see. So let's look at the bottom flange. So we said that to the bottom flange is half the thickness, right? So we'll say equals that divided by 2, right? For the web, equals that plus that divided by 2. Make sure that you're, carrying that over appropriately. And then for this, equals that plus the depth plus that divided by 2. Sound good? All right. Sum of AY over the sum of A. Remember, that's a centroid, right? So if this is A and this is Y, that times that, right? Sound good? Right? Sum of AY over sum of A. So since it's sum of AY over sum of A, I probably need to add all this stuff up. So sum that, and sum that. Maybe I'll put sum here. I don't know, center that up a little bit. Squinch that up a little bit. Okay. So see what I did? So how do I get this, or this number? That times that. How do I get this? That times that. How do I get this? That times that. And again, what happens if I make that bottom flange 1 inch thick? Everything else updates. Okay? That's, again, that's incredibly important when we're in the mode of design, because we're going to build these massive calculators to do the analysis of a given girder, and then, well, man, we got to change that flange size. So we change that flange size, and we want it to update everything else. Okay? So that's really important. All right? So we've got this. How do we get the centroid? That divided by that, right? So I'll just sort of put this down here, and I'll say center of gravity, y bar. And how do I get that? Equals that divided by that. All right. So far, so good. All right. Now, pop quiz. What is the moment of inertia of a rectangle? Who remembers that? Let's give you a hint. It's BH cubed over 12. There we go. Big bunny, Noemi, stop. It's 12. All right. So let's go here. So I'm going to put over here. Let's put recall. And I'm going to call this I sub naught is BH cubed over 12. Okay? So BH cubed over 12, that's the width times the height cubed over 12 for each rectangle. So what I'm going to do is I'm going to compute the individual moment of inertia of each rectangle. But the big thing is I've got to be consistent. Okay? It's width times height. Okay? So for the bottom flange, it's the width, the 16, times that cubed. Okay? For the top flange, the width, 14, times the height, the 3/4. For the web, it's the width, which is this, the thickness, times that cubed over 12. Make sense? Sound good? All right. All right, so okay, so let's start off with the bottom flange. So the width, the 16 times the thickness, the 1.25, so equals, we'll say the width times the thickness cubed over 12, right? And it's, comes out in all these nasty fractions. Here, let's do this. We'll do that. Okay. So, yes. Remember. Good. Well, okay, that's a good point. You're going to see some formulas later in this semester that are pretty hairy. And I probably use way more parentheses than I need. You're right. You're right. When I show you the inelastic LTB expression, you'll throw more parentheses in there just to be happy, because it's not that it's hard. It's it's just long. It's like I would rather just be conservative. So, and technically you're right, but I think what it is because I've gotten in such a habit of those expressions that I just use more parentheses than necessary. So I know that it's going to be the width. The big thing is I want to cube the thickness by itself, so I threw it in parentheses. So, but you're right. So is everybody okay with that? So again, I get parenthesis happy when I use this. It won't make your answer wrong. I mean, if I wanted, I could do this. I could I could go You know, I mean, I could do that and it wouldn't be wrong. I just do it because, yeah, when you look at the inelastic LTB spec or equation, you might start yelling at me. So, well, don't yell at me. Yell at the folks who wrote the spec. So, I'm gonna leave that there since you made the comment. Okay, for the top flange, similar instance. The width times the thickness. All right, so width times, and I'm not going to put the parentheses in. All right. Sound good? Okay. Actually, I am. Now it's bugging me. So, didn't matter, but. All right. Now, when you do the web, though, again, width times height. So it's that, oh, have a negative in there, that times that cubed divided by 12. And what will happen is you'll know you're right because when you do this calc, you'll get really itty-bitty numbers for the flanges, but a big one for the web. Okay? What happens is this. You don't get stiffness per se from the flange. You get stiffness from the fact that the flange is really far away from the centroid. Okay? Now, what do I mean by that? Here's what I'm doing if you're wondering where I'm going with this. I want you to go back and see if you can remember this. Anybody remember this? Probably been a while since you've looked at it. This is called the parallel axis theorem. And this is how you compute the moment of inertia of a shape that's made up of a bunch of individual elements. Like we're dealing with an I-beam that's made up of 3 rectangles. In order to compute the moment of inertia of the whole thing, I need each individual component, which I have. I need the area of each component, which I have, right? It's in the sheet. And then I need D. Okay? Now D, what is D? D is the distance from the centroid of each individual shape to the centroid of the whole thing. So let's just go here. So I'm going to strike an imaginary line right here. We'll say like right here. And I'm going to call this Y bar. So that is the centroid of the whole thing. And when we did the math, we got, what did we get? 17.99 inches. So this is 17.99 inches. Okay? So that's the centroid of the whole thing. These D distances are the distance from the centroid of the whole thing to the centroid of each individual shape. So this distance here, I go like right here, that's D for the bottom flange. That's what I'm after. Thing is, it's actually really, really easy to calculate because of our reference. Okay? We've got the distance from the bottom to the centroid. And we've got the distance from the bottom to the center of this bottom flange. So if I've got the distance from here to A and the distance from here to B, how do I get that? I just subtract. Now, does it matter what order I subtract in? If I do, you know, this minus this or this minus that? No, because whatever value I get for D, what am I going to do to it? Square it. And a positive times a positive is the same thing as a negative times a negative. It'll come out the same. So how do I do this? I go to Excel, and if I want to, oh, I don't need that. I need that. If I want to calculate this D distance, I take the centroid of the whole thing minus that. If I want this one, or nope, wrong one. It's that. What happened there? Let me see something. There we go. That's a little better. All right. If I want this distance, I take the centroid of the whole thing minus that. If I want this one, centroid of the whole thing minus that. And it doesn't matter if I do A minus B or B minus A because I'm going to square it. Okay? So, what do I stack right here? Parallel axis theorem. This plus AD squared. So, right here, equals I plus A times D squared. Copy that down and round that up a little bit because that's getting a little out of hand. Sum that up, and there you go. There's your moment of inertia. 15,969 or so. And that's all she wrote. Sound good? It's not bad, is it? Pretty straightforward, isn't it? All right. The nice thing about this is that I can go through and, I got to change that web thickness. I got to make it 0.5. Boom, everything else changes. Okay? Now that's not a very amazing thing if you're used to Excel, but when we start doing lively distribution factors and strength one moment envelopes and what have you, changing a flange size and getting a whole new set of moments, that's kind of nice. So that'll help out quite a bit. Sound good? Let's go ahead and take this a step further. Let's look at a composite section. Okay, let's do a composite section. So technically, if we're looking at this bridge, we've got 4 sections that we need to consider. Okay, 4 composite sections, because we've got short-term composite sections, we've got long-term composite sections, but we also have interior girders and exterior girders, right? So let's see if we can keep this simple. All right, let's just do one of them because they're all going to be the same except for the width. So let's do this. Let's do a short-term composite section. Let's do an interior girder. It really doesn't matter. We could do an exterior girder. We could do an interior. It doesn't matter. Okay. Let's do a short-term interior. All right. So the short-term interior section is going to look like this. We're going to have, some concrete deck, right? It's going to have some width. And we're going to have the beam. And I'm just going to be lazy and draw the beam like this. Actually, no, I'm going to draw it all out. All right. Couple things. What's the haunch? 2 inches. All right. And we're measuring that from the top of the web to the bottom of the slab. So that is 2 inches. Right? How thick is the slab? For the purposes of what we're doing. It's 8. Because 8.5 is the total thickness, but we're assuming half that's going to go away. We're looking at section properties that we're going to use to compute stresses and strengths. We can't count on that 1/2 inches. So it's 8 inches. Now, does everybody clear on that? That's an important differentiation to make. Okay. Now, short-term interior. How wide is this concrete deck? 10 foot, right? Because for an interior girder, halfway over, 10 feet. And 10 feet in inches is 120, right? So 120 inches. Right? Now, for the purposes of what we're going to do, however, we need to transform that, right? We've got to turn that concrete into an effective lump of steel. Now we're doing short term, okay? So short term means that we divide that width by n, by the modular ratio. And for the purposes of this discussion, we're going to assume the modular ratio is 8. We'll just keep it simple and say n equals 8. So I'm going to take this and turn it, and I am going to be lazy, I'm going to turn it into this. And this dimension is 120 inches divided by n. Sound good? Any questions? Okay. All right. So let's go into Excel. And unfortunately, since we're dealing with a composite section, we're going to need a little bit more input. Okay. We're going to need more data to assess. So let's add some stuff. Let's add a let's add a effective flange width. Let's add, here I can spell that out. Let's add a structural slab thickness. And let's add a modular ratio. All right, and fill that in. So now we've got some new input, okay? I'm going to drag that down a bit. Okay, so what's our effective flange width? It's 120, do we say? 120. Okay. Structural slab thickness is, what is that, 8. And this is 8. All right, let's see if I can center and we'll make this one. Okay, all right. So far, so good? So what I'm going to do now is I'm going to do another set of section properties. So I'm going to build a whole new table. A whole new table, and maybe, I don't know, I'll give it a different color so that we know we're looking at something else. All right. Maybe I'll come on. Move that down a bit. Okay. All right. So now what we're going to do is we're going to do an additional set of section properties, but we're going to look at the composite section. Now, here's an interesting question. For the I-beam, how many shapes did we have? We had 3, right? We have a top flange, a web, and a bottom flange. How many were we going to have for the composite section? I think 4, right? I'm going to say no, we're only going to have 2. We're going to have the slab, and we're just going to have the whole girder, okay? Because we've already got the girder stuff computed up here, and I'm going to shortcut it a little bit. Keep in mind, all my stuff is referenced from the datum. So watch this. So let's look at shape. Let's do the girder. What's the area of the girder? It's that, right? All right. What is the centroid for the girder? It's the 17.99, right? It's this. What's the individual moment of inertia of the girder? It's this, right? So instead of doing that math all over again, just realize that we've already done it once. We don't need to do it again. All right. And let me center all this up too. So we don't need to do that. We can just keep it simple. All right. So those are all the necessary section properties that we need for the girder. What about the slab? Okay. All right. What's the area of the slab going to be? 120 by 8. But what do we have to do? We have to turn it into an effective lump of steel. So how do we do that? We divide by 8. So it's going to be the area, the width times thickness. But we got to divide that by 8. See what I mean? Make sense? All right. Now, let's see if we're paying attention. Y. I'm going to go back to the image. So I want to make sure that we're clear on this. Y. Y is the distance from this datum to the centroid, right? So let's go through this. So how do we get from the bottom to right here, to the centroid? How do we get there? Well, we go bottom flange thickness, the web, the haunch. We don't do the top flange thickness because that's already included, right? The haunch, and then half of this, right? Right? So technically, I guess, if I wanted to be technical about this, I need another input. Oh. I need another input. That way I can change the haunch. Okay? So far so good? So how do I get to the center? I go, let's sort of make sure we're good on that. I go bottom flange thickness. I go web depth. I go haunch. And I go half that. Right? There we go. Make sense? And while we're at it, why don't we go ahead and fill this in? Okay? So moment of inertia. So width times height cubed over 12. But what do we got to do to the width? Divide by 8. So equals, and I'm going to use parentheses, we're going to do the width divided by 8. Then we're going to do times the thickness cubed divided by 12. And again, I'm going a little fast because this is all being recorded right now. So, I can be a little fast with it. Actually, hold on. Okay, it is being recorded. I wanted to make sure it was running. That would have been bad. I know it's late, but I'm going to get some laughs out of you. I promise. All right. So now we've got everything we need to go ahead and just keep on grunting, keep on computing. So AY, remember that's that times that, right? So just, that times that, and that times that, right? And again, I can change that to 1 inch. It changes everything else. So that's the nice part about this. All right. Let's see. Go ahead and sum that up. I might as well just copy that whole thing down. So it equals the sum of that. Sum that. Go ahead and sum that. Let's see. I can clean that up a little bit. Okay. We need to calculate the centroid of this whole section again, right? So this, this term divided by that, right? So since I'm lazy, I'm going to copy this down. We'll say equals that divided by that. And so now the new centroid of the whole, this composite section, put the mouse cursor right in the middle of it, is 40.2. Am I going too fast or are you all good? So far so good? Okay, all right. So what's next? We got to do our d distances. And how do we get that? That minus this, that minus this, so on and so forth. Again, doesn't matter what order we subtract it in because we're going to square it. So doesn't matter. So let's see. Equals that minus that equals that minus that. Last thing, our moment of inertia. How do we do that? Our parallel axis theorem equals that plus area times distance squared. And there we go. So that composite girder's got a whole heck of a lot more strength than the non-composite girder, right? Obviously, you throw more material in there, it's going to get a little stronger. All right. That makes sense? All right. That is a short-term interior set of section properties, okay? Now, what if we were doing short-term exterior? What would change? What's the only thing that would change if we were doing short-term exterior? Flange width. What if we were doing long-term interior? What would change? Instead of dividing by n, we would divide by 3n, but everything else would be the same, right? Pretty straightforward, right? This isn't very complicated. And again, the nice thing about doing it like this is that change a value, everything else changes. Sound good? All right. Here's what I think I'm going to do. I have to meet with some of the senior design students in here for a little while, so I think I'm actually going to call class a little early tonight. What we'll do is next week we'll continue on with this. There's a couple other things I want to do, but I'm going to give you all an assignment where you all build your own section properties calculator. You all do a full-blown calculator in Excel, do the negative section properties and all of that, and then you'll submit the Excel file to me, and I'll test it out and make sure everybody's getting the same properties, and we'll move on from there, because we'll use that sheet for then your next homework assignment where you compute loads and distribution factors and what have you. So we'll keep building on this. So I hope you like Excel. All right, that's all I got for you all tonight. You all have a good evening, safe travels getting home and all that, and we'll see y'all next week.